Good morning, everyone. So this is the 14th lecture, but I'm still some way through the 13th. And in the last lecture, I introduced Ampere's law, which is this. And in this lecture, I'm just going to hit you with a few examples before going on to, electromagnetic induction, if I get that far. So, just to recap, this is Ampere's law, which states that if you have a current I in a circuit or in space, a current density, then the integral around a closed loop is equal to the current enclosed in that loop times mu zero. Okay, so and this is a little bit of a circular argument because this is the example I used yesterday not to derive, but to demonstrate this Ampere's law. What I'm going to do as the first example, I'm going to calculate the magnetic field due to a straight wire, an infinite wire, with a current I flowing through it. And I'm just going to demonstrate the principle. Now, yesterday I did the field due to I did the field outside the wire, right? So what I'm going to do, I'm going to repeat that, and I'm then going to calculate the magnetic field inside the wire due to the current. Bless you. Right. So just to recap, so we know we've got a current flowing through. Right-hand thumb rule gives the direction of the magnetic field, and it's radial. It's not radial. It's azimuthal around the direction, around the current, like that. Okay, and the field lines meet. It's a closed loop. Right. So Ampere's law. I'm just going to repeat what's written up there. The integral B dot dl, so if I integrate the field around this closed loop here, and I'm taking this as a radius r, if I integrate B dot dl, then this is just equal to mu naught times I. Now, as B is constant around that path, I can just take B outside the integral. So the Amperian path is a circle of radius r. Circle of radius r. On this path, B is parallel to the path taken, dl, and B is constant. The magnitude of B is constant. So this integral is trivial, right? It's just I take B outside, integral B dot dl is just B, the magnitude of B at radius r, times 2 pi r, which is just the circumference. Right, so that's the line integral. Therefore, B is mu naught I over 2 pi r for an infinite wire. And this is exactly the same result I got with the Biot-Savart law a couple of lectures ago. So, as for Bio. And okay, so if I start with this method, you can see, because of the symmetry of the problem, it is so much easier to use Ampere's law to calculate the field. I don't have to do any nasty integrals, I just have a simple line integral. Right. Sorry, that should have gone with that, but I drew the figure anyway. Good. So that's outside the wire. So now what happens inside the wire? Okay, so inside the wire I assume a finite thickness. The current I is flowing through it, and again the radius is A of the wire, and I'm going to calculate the field at a distance r, the radius r. And again, all right, because of the symmetry of the problem, right, the field will be azimuthal, like that. It will go round like this. But now this is the really neat thing, right, with Ampere's law. The only bit of current that contributes to this is that part of the current which is inside the loop. So you take Ampere's law literally, it's the current enclosed within this line you've taken. Right. So what we have to do to get the field inside the conductor at some radius r, we have to calculate the current within that circle there, that line. Right, so that means you need the charge, the current density, okay, to get the amount of current within there. So if the current is evenly distributed, throughout the wire, then I can write the current density. It's the wire. It's just a cylinder. Okay, cylindrical shape. So I can then write the current density is equal to J equals I divided by A. It's the current per unit area, which equals I over pi A squared. Right, A is the area of this surface. Right, so that's the current density. So I can now write down Ampere's law for the B field at a radius r. Right, so here's the line integral over the closed loop is mu naught over mu naught times I, which equals, right, now so I've got to express this in terms of the current density, which of course is the integral of J dot dA. It's the integral of the current density over the area. Right, so the current, so this becomes, right, the line integral b times 2 pi r, which is the line integral, equals, so mu naught times the integral from 0 to r 1 over pi a squared. Let me write it down. Sorry, that's I over pi a squared. That is the current density, J, times 2 pi r primed dr primed. And that goes from 0 to r. Now, all I'm doing here is integrating up to get the area of a circle, actually. Now, I think it probably would have been obvious if I'd have just written J dot dA over this surface here. The surface is just the area of the circle. So all I'm doing here is just integrating to get the area of a circle. So it's mu naught I over pi a squared times pi r squared, which isn't surprising, right? That's just the area of the circle. And what also shouldn't be surprising is that this here, pi r squared over pi a squared, is just the fractional area of the cylinder of radius r divided by the cylinder of radius a. So it's just the fraction of the current enclosed within that dotted line. Right. So putting this together, you can see that B is equal to mu naught I, which is that term. The pi's cancel. The r comes from over there, that side, to give 2 pi a squared times r. So that is the current, sorry, that is the field due to the, at a radius r within the cylindrical wire. So this is inside the wire. So what happens is, so if you look at the field as a function of radius r, it's linear, and then it decreases like 1 over r. So, and this is the radius a. That's the form of the field due to a wire. Right. Does that make sense? So the field becomes linear up to the radius, and then it falls off like 1 over r. Good. And but what you've got to get out of this, right, is the Ampere's law. You take it literally. The field is, if you take an Amperian path, as in this dotted line, the only contribution to the field comes from the current that is enclosed within it. The bits outside that sort of cancel to zero. Right. It's a bit of a strange concept, that, but anyway, well, what I've said is good for all symmetrical problems, as this is, right? If you've got any changing currents, if the currents are changing with time, then this has to be modified, and you get a different result. But for steady currents, this is good. Now, so there was the first example, and that's a standard example that you meet in prelims. And this is another one, all right? So we've got a long solenoid. Now, okay, this is like a solenoid. It's like an inductor. It's a loop of wire, like that. And this picture here It's an alternative picture. It's looking at the, sort of looking at the wire from, it's equivalent to this, right? It's just depicting that solenoid there. Right, now, how do you calculate the field due to a solenoid? Now, what we did this, like for Biot-Savart law. Do you remember I calculated the field due to a single current loop, then I integrated over a number of turns of the solenoid to get the field between theta 1 and theta 2, and then I let that go to infinity, i.e. the angle I integrated between naught and pi. Right, I did this a couple of lectures ago. So how do you do this with Ampere's law? I mean, it works, there's a footnote at the bottom. It works provided the solenoid is long. It works perfectly if it's infinite. If it's long, it still is good if you're in a region of uniform field within the solenoid. So what do you do, right? Well, you choose this path which does this. It's a square path like that. And so you integrate, this is now your path integral, and you integrate like that over that path. And notice I'm going through the coils here. All right, so you're actually, there's a current I flowing in here. So if you've got n turns of wire, then you cross n times the current as you go along this path. Right, now it's really neat this, because what you just use the Ampere's law literally. So you've got this surface here, this line, and you let this go to infinity, right? You just shove that line off to infinity. So of course these lines are going off to infinity as well. And so there's no contribution. At infinity, there'll be no contribution from the field due to this solenoid. So the line integral along there is 0. All right. So now, but this path here, going that away, and that path there is going that away. And because of symmetry, the contributions from them must cancel. So if you do have a contribution from that, it's going to be equal and opposite to the contribution due to that one. Right, so all you're left with is the contribution due to that. Now, it turns out anyway that for a solenoid, the field is completely along the direction of the solenoid. So anyway, there is no field. If you've got an infinitely long solenoid, there's no field out here anyway, but you don't a priori know that. But in any case, those contributions are going to cancel due to the symmetry. So this is side 1 and that's side 3. Sorry, that's 2. What did I do? 1, 2. That's side 2. That's side 3. So you take side 3 to infinity, i.e. does not contribute. That's gone off to infinity. Sides 1 and 2 cancel due to symmetry. Right, so we're just left with this third side, this fourth side, sorry. So contribution due to side 4. So this is the one that we have to calculate, the integral b dot dl over the 4 sides, 3 of which give 0, is equal to b times l. which equals mu naught n times I, which is, this is Ampere's law, all right? And this line integral between there and there is just the length, is b times the length, you integrate over, and then is equal to mu naught I. Now, notice n, right? N is the number of turns of the wire. Within the Amperian surface. Okay, now, so you have to take this literally. You know, when you do this integral b dot dl is mu naught times the current. If you've got certain, loops of current, you have to take each, you have to sum up all the loops within the line. Right? So there's your surface, there's your contribution to B along there, and this gives you B equals mu naught n over L times I. Now, this was exactly the same as I got for the Biot-Savart law, with about 2 boards worth of working. Okay, so same as for Biot-Savart law. Good. So that's so you can see it is so much easier using Ampere's law. Good. So the final one is a toroid. I don't know if you know what a toroid is. A toroid is like a solenoid, but it's something that comes back on itself like that. And it's got current I flowing through it. So it'll have some terminals here. Right, so that's a toroid. And the toroid has n windings, okay, and each contain each winding, there are n windings, each obviously has a current I flowing. I should have said actually, and maybe it's obvious, right, that I could have taken this Amperian path right close to to these coils here, these turns, or I could have taken them close to the bottom. So it doesn't. So that means it doesn't matter where I take that path. I still get this same result, which means that the field is constant within the solenoid. That, it's uniform field within the solenoid. I should have written that. And that just comes out from the fact I could have taken the path here or there, and I get the same result. So uniform field within solenoid. Good. Right. So now I come to the toroid, and the same applies. Here's my Amperian path, straight through the middle of the toroid. So the Amperian path inside the solenoid cuts current carrying loop, n times. Right, so here's the path, and so I can trivially write down integral along that line, which is within the within the coils, I should say that this has a radius r. B dot dl is b times 2 pi r, which is just the circumference of the path, is mu naught n times I. So n, because I have n turns of current, which gives b is mu naught n I over 2 pi r. Right, so that is the field inside a toroid. It follows a circular path, obviously, and it's the same everywhere. It's uniform within the toroid. But hey, look, if I take a path out here, outside the toroid, all the current loops add up to 0 within that, outside there or inside there. So actually all the field is within the toroid itself. Right. So it's quite a cool law. Here's the summary. I don't want to dwell on it. It's just so you've got it all in one place. There's Ampere's law. There's the Gauss law of magnetism, which I did yesterday, and I've just summarised all the formulas for the various what's-its. Good. And so I'm half a lecture behind. And what I'm going to do now is just summarise everything, everything we've done about magnetostatics, i.e. steady currents, and then I'm going to come on to induction. What induction is what happens if we have varying currents, time-varying currents. Then we start inducing things like other currents. Right. Good. There's no way I'm going to get through all that. I'm going to do the conservation of charge, which is a bit, I'm just randomly throwing that in at this point. Current density and Ohm's law, vector and scalar potentials, that's off syllabus, but just I thought I'd just mention it. And then I was just going to summarise where we've got to before getting on to induction. Now, if I can get to 14.5, that'll be good, because then I'll start on induction next time. Good. Now, conservation of charge. Now, everybody accepts conservation of charge. Well, in electromagnetism, there's a vector formula which is all you need to know about charge conservation. And so I'm just generalizing things. So if you've got a volume V here, so there's some volume V, and there's like current flowing out of it. Right, this is J means current density. It's current per unit area. And it's flowing out of this surface A. And here is a small element of surface. So obviously, if you're flowing current out of this enclosed volume, you're losing charge from the volume. Right. So we consider that volume bounded by surface S. Right, so I'm just going to write down this, the integral of current density. So if I sum up the current density flowing out of or into the surface so J dot dA is equal to the charge lost. From the volume, all right, by the volume, per unit time. Now, if you think of the definitions of all this stuff, it'll be obvious. J dot dA is the current through the area dA from the volume. Charge per unit time is current by definition. So charge per unit time is current, and so you're losing current. So you're losing charge from the volume through the area, and because you're losing it, you pick up a minus sign. All right. So the integral J dot dA, which is the current, is just the current. Current is charge density per unit. Is the charge density over area is equal to minus dq by dt. All right. So you're losing the charge from the area. This is the charge within the area, which in terms of charge density, d by dt, the integral over the volume, rho v dv. Right, so this is the charge density. I integrate the charge density over the volume to get the charge, and then I differentiate with respect to time to get the current, which equals J dot dA. All right, in terms of the current density. And I've picked up a minus sign because I'm losing the charge from the area, from the volume. So this is a statement of the conservation of charge. I haven't derived anything. It's just a statement that charge is conserved. Good. So I'm going to use the divergence theorem. Bless you. On left-hand side. So the divergence theorem on this gives me the divergence of the current density over the volume then equals minus d by dt integral v rho v dv. And hence I can equate these terms. This gives the continuity equation. This is the equation that you will meet in the second year. The divergence of J is minus dt, the rate of change of the charge density. Right, so that's the continuity equation. And it's just a statement of the conservation of charge. And you'll, we'll meet that in, you'll meet it certainly in the second year. And this is just a summary of what I've said. There's the continuity equation. Interestingly, right, so this is the continuity equation. So for constant, so for steady currents, dj by dt is naught. So dj by dt is naught for steady currents. I think this is obvious. If you have a steady current, then J is, the current density is not changing as a function of time. So this gives constant B fields. The B fields don't time vary. Similarly, d rho by dt is naught. This is for stationary charges. All right, which means constant E fields. So this is all electrostatics and magnetostatics. Constant E fields, constant B fields. And of course, this would lead to, in this case, the divergence of J being 0. If in this case, right. So I'll write in this case. Because we will, next lecture, be considering time varying currents and charge densities. Right. So this stuff you'll have done in circuit theory, but just to tie in the this course with circuit theory, I can write Ohm's law as V equals IR. So we've got some conductor there represented by that cylinder. We've got an electric field. We've got a current. We've got current density. Through an area at the end, we've got a length L. You probably even did this at A level. The voltage provided by the battery across the length is just given by the electric field times in the conductor times the length. And the current, of course, is the current density times the area by which, the area of the conductor. So you put all this together. EL, which is just V, is IR, which is JAR. Whoops, JAR. JAR is just I. Oh dear. So EL is JAR, which gives Ohm's law. In terms of current density. Okay, and so J equals, this is just Ohm's law written in terms of the current density and the electric field across the wire. Right, so this leads to the definition of conductivity, which you often see in prelims, and you always forget what the hell it is. It's this. Its conductivity is the length divided by the resistance times the area, which is then the reciprocal of the resistivity, which again is I call it rho, is 1 over sigma. Is RA there. Good. That's just, again, a bit of an aside. Now, off-syllabus alert. It's only one slide. I did mention it before. I mean, for those that are interested, indeed, I don't think you hit this in the second year either. It's off the second year syllabus too. You probably will meet it in the third year in terms of the symmetries course. And you certainly meet it in quantum electrodynamics, which is where the vector potential is used frequently for the photon field. But I think that's a little bit of a digression for this this particular course. So it's just like you define a potential, right? So in electrostatics, there's the field. Just remember it, right? The E field is grad V or minus grad V, where V is a scalar potential. By the nature of the magnetic field, there is an equivalent potential, but it's a vector. And you drop the minus sign and you take the curl of it to get the field. So A is the magnetic potential defined by that. And if you want to ignore this from here on, you can. But it's and there's always a potential that exists because, remember, the divergence of B is 0. I did that yesterday. And so you can always define a curl of A where you take the divergence, which will be 0, because that's a vector identity. So this is you can always define the magnetic potential. If you stick this into Ampere's law, I mean, if you forgot what Ampere's law is, it was in vector form, or rather vector calculus form. It was this, and I did it yesterday. Mu naught J. It's just a different form of Ampere's law. Then you stick the vector potential in there, so you have a curl, then you've got this vector identity here. This is a really important vector identity, by the way. It's one you've got to remember. You've got to remember that one. Actually, it's in the data sheet, so you don't have to remember it. But it's you'll meet that vector identity lots, and this gives you. This equals mu naught J. Now you set the 0 of electrostatic potential V. You can set that to be 0 at infinity. The choice is, and this is known as sort of a gauge theory, actually, which is a bit over the top for this lecture. But you can arbitrarily set the potential that you want where you want it. So if you set the divergence of A to be 0, that is a choice you make, and you do this in quantum electrodynamics as well, and you get Poisson's equation, right, for magnetic fields. So this is Poisson's equation, which, if you remember rightly, was del squared V is, oh gosh, I forgot what it is now. It's epsilon naught rho, I think. And it's rho over epsilon naught, I mean. So this is Poisson's equations for magnetostatics. It's got complete symmetry with the electrostatics case, only that current density is a vector. All right? Before we had charge density, which is a scalar. Okay, and I don't want to get into magnetic scalar potential. That's going one step too far, but you can actually, as the vector potential is the standard one, but you can actually define a magnetic scalar potential, which can have useful applications. It makes for calculations quite a bit easier. The trouble is that if you, with the electric potential, this is conservative. So if you if you do the force along a closed path, you do no work. It's a conservative potential. This isn't conservative. It's totally dependent on the path you take. So you've just got to be aware. The curl of B is not equal to 0. But you're not going to do any calculations using that anyway, so you don't really care much. Good. You know, I'm probably going to get on to magnetic induction now. Because what we've done, all I'm doing is summarising where we're at. So we've done Coulomb's law. Now, you know, it's a question of making something very easy, really looking rather complicated. But I've expressed Coulomb's there in terms of a charge density. This is just Coulomb's law. The force is 1 over 4 pi epsilon naught r squared. It's just that times q. So it's q over 4 pi epsilon naught r squared. It's r cubed because I don't have unit vectors here. I've got a little diagram there, what I mean by those. So that's the general form of Coulomb's law. So an electric charge generates electric field. The field lines either end up on a charge or infinity. They don't end in midair. Right. So this leads to Gauss's law in integral form, where E dot dA is the charge enclosed divided by epsilon naught. We did loads of examples of that. And then I showed how to get that in differential form by using the divergence theorem. And that is, that is one of the Maxwell's equations. Right, so that's, the field is conservative, so we can go from one part, if you've got electric fields, you can go from some point, taking a route, dragging a charge along with you, and coming back to the same point, and you do no work against the field because any work you put in, you get back. It just means that it's conservative. So this gives you the curl of E is naught. Right, which is not, it's not one of the Maxwell's equations, but it's a bit of, it's almost, it's the Maxwell's equation without any time varying magnetic fields. Right, so that's all about electrostatics. So magnetostatics, we've got an equivalent law as for Coulomb's law, but we've got this time, we've got a current density. This is due to a current, and the current density is a vector. So this gives a vector field, but we have a vector integral here with a cross product. Right. Unlike for the electric field, the magnetic field has no magnetic monopoles. The magnetic field lines form closed loops, and this is just because the magnetic fields are always perpendicular to the radius vector to the current that's causing it. So they form these closed loops. Right, and the Gauss law of magnetostatics, this is again they only form closed loops. So the integral of any surface about a volume, there's many field lines coming in as going out. So that's just a statement. There are no monopoles. Right. And in differential form, you get that. That's one of the Maxwell's equations. Ampere's law, which I didn't derive, but I just indicated examples of where it works and showed it was equivalent to Biot-Savart. You integrate around a closed line, a path, and that closed line is just the current enclosed within it. Now, all right, I haven't done any nasty examples yet. I will do some nasty examples. You might ask, well, you know, if you actually move this surface, if there's a current flowing here but a gap there, I'm going to get a different result in that gap, and you'd be right. And that's when we have to take into account time-varying electric fields, which is what we're going to do next. So this is all good for constant currents. Right. So yeah, there's nothing wrong with Ampere's law. It still holds good, even if you have breaks in the circuit, but you just need to modify it. Right, so there's the Ampere's law. Here is the equivalent vector calculus equation, the curl of the B. Curl of B is mu naught times J. And then we have the continuity equation, which is just the conservation of charge. Right, so that's a good place to stop. I'm going to zip through the next... I'll completely zip through these slides in like 3 minutes. So I'm back to where I should be. Must have caught up half an hour. Anyway, so see you Monday. Thank you.